Hello, everybody. This is Ajay. I would like to showcase the project that I have developed and walk you through a quick demo. Let's go. Okay. I have named my application as the food storage parameter tracker. So, basic idea of the project is to measure different parameters where a food is stored, so that you know, based on different metrics, you can take a timely decision. So let's see what it is. This is the agenda for today. I'll be walking you through the overview, talking the idea of the project and some of the use cases and high-level architecture, some of the edge and the cloud components to it, and I'll give you a detailed demo. And then we'll go over the software solution that I've built, what are the different components of the software built and some of the features that I've built specific to IoT, and then some services that I've used on the cloud provider. And I'll also talk about some of the challenges that I faced and the solution I came up with during this process, right? Yeah. Why do we need this application? As I mentioned, this application is used to track different parameters in um, a place where food is being prepared or maybe food is being stored, right? So first is food safety. Let's say there are some perishables like seafood or maybe some other item that needs to be stored at certain temperature and humidity. What happens due to some technical error that temperature is way off than what it is supposed to be, right? In that case, the food goes stale and maybe it could also be a very expensive, right? So how about a solution where you could monitor that parameter, and if a temperature drops to a certain level or maybe a humidity drops to a certain level or increases, you get notified and you can take timely action. And the next is inventory management. Um Imagine being serving your customer and then realizing that you are short on some items, right? Uh, so it would be really beneficial to know if an item is getting very low in quantities in advance, so I can order it in advance, right? And smart management of the place. So let us say it is a fast food joint, right? And the joint manager can have an access to a dashboard where he can see or monitor all of these parameters and take a timely decision, right? So let's talk through the high-level architecture. So as you can see here, we have two components. One is the edge and one is the cloud. So for this, I have used AWS as the cloud provider. I've had experience on Azure developing an enterprise solution and also AWS cloud working on IoT here. So the reason I choose AWS is because I wanted to showcase MQTT communication specifically. Um, you know, Obviously there is it Azure provides that feature as well, but since we use an SDK, it is all wrapped under that SDK, and you can't really see that topic subscription, topic creation, publishing, and things like that. So AWS makes it really simple to showcase that concept. And the next thing is I'm not running any compute heavy uh, workloads on the edge. So it is a fairly simple application, and I chose to use AWS IoT Core, which is very apt to this use case, right? Okay, so talking about the edge, I have a Raspberry Pi, and Raspberry Pi is connected to a temperature and a humidity sensor. In this case, Raspberry Pi acts as a gateway device. It directly has a communication with AWS IoT, like receiving and sending telemetry data. And AWS IoT also facilitates in registering these devices. So here is, if you can see this, right? So this is a Raspberry Pi, and I have a DH-T22 temperature and humidity sensor connected to this. And then there is a node device. I have used ESP8266 as the node device to communicate with the Raspberry Pi. And this node sensor is connected to a ultrasonic level sensor. So here is the yeah, so this is the ESP8266, and this is the ultrasonic sensor. And the communication happens between the gateway device and the node device locally. That means the node device does not have any communication to the cloud whatsoever. All the communication happens through the gateway device, and these two devices are locally connected through MQTT, and I use MQTT broker to establish the connection and the communication, right? And also then there is a web interface where you can request for on-demand data from these devices, and also you can get alerts notified on the dashboard. Uh, you know, so the dashboard, I could not develop a view for the dashboard, so there is only a backend for it as of now. So you could see the message is getting received, and you can also request for on-demand data. Now, going to the AWS cloud side of it, the major component is the AWS IoT, which is again a layer between the physical device and the cloud. So it helps in device registration, and as I mentioned, telemetry to and from the device. And also AWS provides a cool thing called as IoT rules, where you can based on the incoming data, you can perform some business actions. So, for example, here you can see it sends the data to a Lambda function, which process the raw data and dumps it into a S3 bucket. And then there is a streaming data that comes in and gets written into a DynamoDB table. And then based on different parameters, an alert is set, which republishes to a topic and sent it back to the web interface. Yeah, as I mentioned, these are the high-level components. Raspberry Pi connected to a temperature humidity sensor, ESP microcontroller connected to ultrasonic sensor. Um, so what the Raspberry Pi does is, along with the temperature sensor, is it measures the humidity and temperature, which is very apt to be used in a place like a fridge, where you would want certain perishable items to be monitored there. And the ultrasonic level sensor could be used to measure the level of a liquid. It could be maybe a cooking oil, maybe a sauce, maybe a soup that is created. So yeah, these are some of the use cases where I can think of using this. Yeah, so let's see a quick demo of all of this working. Hi, this is a setup. I have a Raspberry Pi which is powered through a micro USB, and then there is a humidity temperature sensor connected through the GPIO ports. And then here I have the Node MCU connected to the ultrasonic temperature sensor. So, this is basically measuring the level of the liquid here. As you can see, full to half here. It uh, gives me the reading in centimeter. Again, this is powered through a micro USB cable. So this is uh, the setup. Hi, I'm going to demonstrate an on-demand request coming from the web server. So as you can see here, I have opened up a web server, and since I don't have a view with a uh, button that I can request on-demand data, I just have simulated it, with a timer here. It calls the on-demand function every 10 seconds, just mimicking pressing the button every 10 seconds. And then the request from here travels, it basically publishes to a topic. The request travels through AWS IoT, goes to the Raspberry Pi. I have SSH into my Raspberry Pi here. So the Node app will be running here. It gets the message. It then triggers Arduino to get the level data. Then level data is sent back to Raspberry Pi. Raspberry Pi aggregates the data and publishes it back to a topic, travels through AWS IoT, and the web server receives it. So this is the flow. I'll show you how this works. First, let me start the software, then the device software running on Raspberry Pi. So this is connecting to the MQTT broker. AWS IoT core, it is connected, and the software on ESP is already running. Now I will fire up the web server. It's connected to IoT core now. Yeah, so it is sending a on-demand request, and then it also received. So after sending the request, it travels to the AWS IoT. I just started a test client here. So as you can see here, it is sending a request, on-demand request. From there, the request goes to Raspberry Pi. See on-demand request requested. From there, the request goes to the Arduino to uh, get the level sensor. It received a message in this topic with the type on demand. It calculated the distance. It is publishing it back to the MQTT topic with, sending back the data and the level. Raspberry Pi received the data here. It aggregates, humidity data, temperature, level data, and it publishes back to the web server. So when it publishes, it travels through AWS IoT. So as you can see here, this is the topic that it publishes to. This is the payload. We have the on-demand request, device ID, humidity, temperature, level, and the timestamp, right? So once it goes through AWS IoT, it ends on the web server here. So as you can see here, the data is received and the the liquid is half. Uh, yeah, this is the level of the liquid. So the temperature is being displayed in degrees centigrade. I think RH is relative humidity, I believe. Yeah, so this is on-demand data request demonstration. Yeah. Now I'll demonstrate how the telemetry is streamed to the cloud. So starting the device app on Raspberry Pi. So connected to the broker, IoT core. So it actually published a request to the ESP, got the data, aggregated it, and published it back to AWS. So as you can see here, I have subscribed to that topic, stream topic on the MQTT client here. I'll clear this. So every 5 seconds, you will receive the data. So stream data. Every 5 seconds, you will get the data. Right. So also another thing I wanna show here is going into rules, right? So whenever there is a stream data coming in, I have a store to DynamoDB uh, rule written. So what it basically does is it listens to this topic, grabs these values, puts that into a DynamoDB table here. Uh, going to So this is a device data table with device ID as the primary, the partition key and the timestamp as the sort key. Going here, exploring data. Ah, I think that's not right. Okay. Yeah, this one, as you can see, this is the current data. I have the device ID, timestamp, temperature, humidity, and level. So this is, yeah, the timestamp is again a stringified UTC time, and yeah, the month or the year is not delimited with any characters, so it's just a plain string. Yeah, so this is the demonstration of streaming data. Okay, now I'll demonstrate a batch telemetry to upstream. So yeah, the upload to upstream is complete. Upload to upstream is complete. So I have taken an example of uploading to batching the data every 10, 15 seconds or so. So yeah, this is what happens. So once it is published to a topic, so basically what happens is that all the data which is written in a file gets read, uh, compressed, and then sent to the cloud. Now going here, I have a rule written which says batch telemetry to Lambda, right? What it basically means is grab everything from all messages from coming in this topic and then trigger a Lambda function, right? Going to the Lambda here. Yeah, so this is my Lambda function with the trigger as AWS IoT, and there is a custom role that I created with S3 put permission, and also it has CloudWatch raw logs policies attached. I will. So this is the CloudWatch logs. If I go here, as you can see, okay, it received an event. So this event is the compressed data. As you can see, it is just a string. Okay, this is not Okay, this is the okay, looks like there is a small bug. I was supposed to send a string, but I did not stringify it. There is object being sent. But I will show another data that is getting parsed, an old data. If you probably see this one, this example. Huh. Where does it say? Okay, yeah, here is a good example. So as you can see, the compressed data comes as a base64 encoded string. After decoding it, decompressing it, this is the data that was sent from the device, batched data. So that this gets written into a S3 bucket. Uh, Pulling up the bucket here in a minute. Okay. Oh, this was DynamoDB. Yeah, so as you can see here, this is a CSV file. If I open it, yeah, this is yeah, the data getting written into a file and dumped into a S3 bucket. Okay. So yeah, this is a demonstration of how the data is batched and sent to an upstream, and then from there it is dumped into a cold storage. Now I'll demonstrate how an alert is raised and pushed to the web service. Before that, I have filled the jar up to the brim, and it shows at the level full. Okay, running the web service, the Node app. So as you can see, I filled the jar to the brim. It says full. Now what I'll do is I will take out some water away from that, and if it goes to the level that is marked as low, it will trigger an alert. Yeah, as you can see, we are receiving the level alert. It says source level is at XYZ centimeter, and the device ID associated with it. So yeah, this is how when the liquid level goes below certain threshold, it triggers uh, an alert. So yeah, this is the alert here. Okay. I will now walk. I will now walk you through, the software solution, some of the features that I've implemented. So as you already saw in the demo, right? Uh, I would consider this a fairly simple IoT application, but I have designed this in keeping in mind, what are some of the IoT features that I can showcase here, irrespective the size or the scale of the IoT project. These features that I've implemented are very critical in any IoT solution that we design. So let's go over that. Yeah, so the sensor interface, right? So the Raspberry Pi is connected to a temperature DH322 sensor. It is connected via GPIO ports, and the communication happens locally via serial communication. And then there is ESP8266 node MCU, which is again connected to the ultrasonic sensor. It is used for measuring liquid levels, and the communication between both happens locally over MQTT topic, right? So the next is connectivity. AWS IoT is the major player here, which connects the physical world to the cloud. So it provides features like registering and the provision device. So I have registered Raspberry Pi as a thing, and also I have registered the web servers as a thing. And it facilitates communication from the device to the cloud, cloud to the devices, and perform any telemetry receiving actions. And then it has AWS IoT rules where I can, based on certain parameters from the incoming telemetry message, I can take certain business actions. And then there is the Mosquito MQTT, which is installed as a broker on the Raspberry Pi, and the Node MCU or the ESP8266 acts as a MQTT client connecting to the Raspberry Pi and communicating with it locally. Yeah, and this is one of the significant feature. How is telemetry handled in this project? And this is apt for any IoT project that could be built. So one is streaming data. Um, So I collect data from these sensors at a certain interval. In my case, it is around 5 to 8 seconds. Um, I read from the sensors, and I send it upstream via a topic. And then there is batching data. So let us say there is a use case where I the data to me is not that critical, and also there is a bandwidth constraints at the edge, right? So I can batch that data. In my case, I am writing that into a file and send it to upstream every interval. So this could be every midnight, maybe once a week or once a month. I also implemented a compress feature here, and also it provides significant bandwidth, um, uh, lessen in bandwidth usage. I compress the data and send it to upstream. And also another feature I wanted to specify on the streaming data is streaming data. That feature could be used where an application that needs data which is very critical to business needs. Um, you know, there is no time delay. So as and when the data is read, it is being sent uh, to a destination, right? And then there is a on-demand data. Uh, so as you saw, there is a web server or the web dashboard I have created on click of a button. I can request for data to be read from the sensors and sent back to be displayed on the dashboard. So this is a on-demand feature that I have implemented. Yeah, so this is how the on-demand request actually works. So on click of a button, the web app publishes to a topic, and then the Raspberry Pi, which has subscribed to that topic receives that message, and it triggers a data read from the ESP8266. ESP8266 publishes the data over a topic which the Raspberry Pi is listening to. Raspberry Pi now aggregates temperature, humidity, and the level data, and publishes that data over a topic, and web app which is listening to that topic receives that data on demand. So this is the whole cycle of, right from the button press to data getting received on the dashboard. Yeah. So the next is uh, how does a streaming or a batching of data works internally? So I read data every 5 seconds, publishing and subscribing through a topic. And then once the data is received, I aggregate them, write it into a file. Along with that, through this the stream topic, I publish the data which acts as a streaming data, and then there is a separate topic for my batched data, which I send it every a certain interval. So this demonstrates both the streaming feature of the telemetry and also batching feature of the telemetry. Yeah, and yeah, so far you've seen some of the features like how the telemetry is handled, how the connectivity on for the device and the cloud is handled. So I'll walk you through some of the rules and the alerting mechanism. For this, I'm leveraging AWS IoT rules, which does most of the heavy lifting here. So when I am getting a stream data pushed to upstream, I trigger a rule. The rule which listens to that topic. What it simply does is it grabs the data from that topic and writes it into a DynamoDB table, right? And then there is a alerting mechanism. There are two rules that are created, one for temperature and one for level. Uh, you know, if the temperature is above certain above or below certain threshold, a trigger is um, raised or an alert is raised. The same happens with level as well. So how this basically work is the web app is subscribing to the alert topic. So whenever there is an alert, the IoT rule publishes a message to that topic, and that message is displayed as an alert on the web app, right? And the next is what happens to the batch data that I sent. So again, IoT rule listens to a topic which where a batch data is coming in, and then it will trigger a Lambda function. So the Lambda function basically it uh, decompresses the data, writes it into a CSV file, and dumps it into a S3, and that is considered as a cold storage here. Yeah, so and ESP8266 software, it's written in Arduino, which is C, C++ based, and it collects a level sensor from ultrasonic sensor, and then there is a web app, actually a web backend. I was not able to implement the view for it, the buttons or the notification boxes, but the backend is functional where you still can trigger on demand request, you still can receive alerts in real time. Okay, now let's talk about the cloud infrastructure. So as I explained previously, why I chose to use AWS as compared to Azure. Uh, the it helps in communicating with the devices, registering the devices, and then there is the Lambda function, which as a Node.js runtime, and the basic use of this Lambda function is to process the compressed telemetry. It decompresses and dumps it into a CSV file, and which goes into a S3 bucket. And S3 bucket it is used as a cold storage. Um, and then there is a Dynamo DB, which can perform active read writes and acts as a hot storage where the telemetry is saved as and when it is received. Yeah, so I took some time to develop the solution from scratch, and I certainly did go through some challenges, and I'll walk you through what were those challenges and some of the solution that I came up with. So the first one is connectivity from the ESP to Raspberry Pi. Because my use case was I wanted the communication to stay local. I could not use AWS IoT, which would mean that any data from the ESP would go to the cloud, come back to Raspberry Pi. So I used Mosquitto MQTT broker, which made the Raspberry Pi as the broker and the ESP as the client, and the communication is established locally, right? And another point I would like to mention is, as you already know, I'm using AWS IoT Core, but you could actually use the AWS Greengrass, which would eliminate the use of using the Mosquitto MQTT broker, and it internally provides a feature of connecting node devices to the gateway devices and establishing a connection. So that's a good improvement over this, in my opinion. And then there is a Lambda to S3 writes. So since I created the Lambda function with basic settings and a basic execution role, the writes weren't happening to the S3 bucket. So I had to create a new role with a policy attached, which has a S3 put permissions, and I attached that role back to the Lambda function, which solved my problem. And then there is the ESP firmware issue. So initially, I wanted to write the ESP software in MicroPython, which I am more comfortable than Arduino programming. So while uh, doing that, before I write any software onto that microcontroller, you need to flash with the firmware. And while I was trying to flash it with MicroPython, I actually burnt my microcontroller twice, and I didn't want to risk it doing it again. So I switched to using Arduino programming, and I reflashed it with a stock firmware, and yeah, that is how the software is developed for ESP. Yeah, so this is pretty much it. This is what I wanted to showcase and talk about. Uh, yeah, feel free to ask me any questions. Also, I'll be sharing all the recordings, the presentation, and the demo videos, or even the GitHub links to all the code. Yeah, feel free to reach out to me if any questions. Thank you.